Now in this last video on the topic of basic object types, we will be concerned mainly with lists. Here again is our overview from the beginning, where we see that there are two basic types of vectors: atomic vectors on the one hand and lists, also called generic vectors, on the other hand. So lists are the second major type of vectors, and in order to get a consistent naming as compared to atomic vectors, lists are sometimes called generic vectors. However, lists are the more common name used to describe these kind of data structures. The difference to atomic vectors is that they can contain objects of different types. Please note, atomic vectors were actually defined by the fact that they can contain elements only of one particular type, so that is why we actually use the subtype of an atomic vector to describe its type. So an atomic vector that only contains elements of type double was called a double vector or double atomic vector. An atomic vector that only contains elements of type logical was called a logical vector or logical atomic vector. We can't do that anymore with lists, because lists can contain objects of different types, so usually we say that a list is basically a list. To see that, the type of list is always list. Let's check out this example here actually to see what is meant by this. So let's go here into our studio, define the list that I just described, and if we use our function typeOf to actually assess the type of the list, we see that it is of type list. But we also see immediately here from the definition that the list is much more complex than what we have seen in the context of atomic vectors. So a nice way to get a more detailed overview of what kind of list you are actually dealing with is to use the function str, which actually stands for structure. And you can apply it to the list we defined above here, and you see a number of information that was not necessary before. So you see we have a list of 3, meaning that we have a list with 3 elements. The first element is a numerical atomic vector containing the elements 1, 2, and it has length 2. The second element, this is this vector here, is a vector of type character, also of length 2. It contains the element A and B. And the third element, this is this one here, is a logical atomic vector that contains 3 elements that contains true, false, false. So you see, not only can lists contain elements of different types, they can also contain elements of different length. And because lists are much more complex in this sense than atomic vectors, something that you will use much more frequently in the context of lists than in the context of atomic vectors is naming the different elements of lists. To see how this works, I prepared this example here. So let's define the list L2, and we can retrieve the names of a list using the function names. If we call names on list 2, we see that the elements of list 2 have 3 names that were given explicitly to this list. They were given by creating the list using the function called list, and then first writing the name of the elements as a character vector, then using the equality sign, and then adding the actual element. Then with a comma, you separate the first element from the second, and again for the second element, you start by providing the name as a character vector and then providing the actual element. Now you can retrieve the elements of a list by calling them by name and by using the indexing that we already encountered in the context of atomic vectors. So you could retrieve the second element of the list by writing L2 square brackets letters. But what might be a little bit counterintuitive here is that if you execute this, you get the result in the form of a list. So if we check out the type of what we actually get here, we see that it's a list. And you might be surprised because actually when you check out the structure of L2, you see that letters is of type character. Now here you see one important difference to atomic vector when it comes to indexing. If you really want to retrieve this this vector here, you do not need to use single square brackets, but double square brackets. Now, if you retrieve the second elements like this, you actually get the underlying atomic vector, something you could also verify with a type of function. So, actually, indexing works a little bit different for lists. If you want to get an element of a list as a list, then you use single square brackets to index lists. However, if you want to have the underlying data structure of the element of a list, then you need to use these double square brackets here. There's also a nice shortcut that you might use, this $sign here. Then you also get a preview if you type it. Then you can extract the elements directly. But I think using the double brackets is a little bit more formally correct in a sense, but because of the ease of typing, most people actually use the $sign. This is just something you should definitely keep in mind when working with lists. And this also brings us to our last topic concerning lists, the practical difference to atomic vectors. There are actually two main differences that are important in practice. First, vectorization does not work for lists, and second, indexing works differently. We already discussed the second one just before. Now I want to say something about the first one. This is something you could actually try out yourself. First, define a vector with the numbers 1 to 3. You want to multiply every element with 2, so you can actually vectorize this by writing 2 star name of the vector. But if you define a list actually with the same elements and you want to do the same vectorized operation on lists, you will see that this doesn't work. And this is actually the main reason for why people usually want to use atomic vectors, because they allow for the concept of vectorization. The reason is that if the computer gets an atomic vector, it already knows only by looking at the first element what the types of the other elements of the vector will be, because atomic vectors can only contain elements that have the same type. A list, however, can contain elements of different types, so by only looking at the first element, the computer does not know what the other objects or the other elements will have a type. So it definitely really needs to check every single element, so the concept of vectorization doesn't make sense for lists. The second concept has already been before. If you extract an element of a list by a single square bracket, then you get a list. However, if you use the double square bracket, you actually get the underlying data structure. After seeing this, you might think a little bit about lists. Why do I need them at all? So atomic vectors seem to be a little bit cooler, so I can use this concept of vectorization. Maybe indexing is a little bit more intuitive. Well, lists are more general. They are more generic. That is why they are sometimes also called generic vectors. So they are fundamental to many more complex data structures that we will encounter later. But before we move to these more complex data structures, I want to make some remarks on some strange object types. So there are two strange data types, NA and null, that we already encountered before. NA is used to represent an absent element of a vector, or absent elements. So that happens frequently when vectors contain, for example, observations from an experiment where people were asked to answer questions, but a person didn't answer one particular question, say the second question, then the result you get for this is missing. And for R, it's important to keep indexing straightforward, to actually have a data type indicating that this element of the vector is missing. Many functions behave differently when NAs are present, and we actually already figured this out in the context of the optional argument NARM. So if we apply the function mean to a vector that contains a missing value, we always get a missing value as a result. However, if we use the optional argument NARM, actually R first filters out missing values and then computes the mean. If you want to test whether something is an NA or is a missing value, you can use the is family of function simply by using is NA, and check whether a vector contains any missing values. You can use the function any NA, which provides you with true if there is at least one missing value in the vector you are studying. The second strange data type is null. It's in fact a data type in itself. We saw this in this overview at the very beginning. In practice, it's actually best thought of null, of nothing, of a vector of length 0. So if you create a vector only by calling the function c, then you will get null. So the type of null, as you might will see, is null. The length of null is always 0, and you can test for null using the is family of function by calling is.null on the vector. When do you use this kind of strange vector? There are actually two instances. The first is if you want to represent an empty vector of arbitrary type. So you just want to say, okay, there's an empty vector. I don't know whether this is becoming a character vector, a logical vector, or a double vector. Then it's best to use null. Or it represents an absent vector, so a vector that is currently missing. That is not the same as NA, which represents an absent element of a vector. Null is really to denote the absence of a vector itself. Okay, so at this point of time, it's probably a good idea to wrap up what we've learned about basic object types so far. We learned in the very beginning that everything in R that exists is an object. And in this section, we learned that the most important kind of objects are vectors. There are two basic vector types, atomic vectors on the one hand and lists or generic vectors on the other hand. Atomic vectors only can contain elements of the same type. So we usually say that the type of a certain atomic vector equals the type of its elements. There we discussed four main types: logical values, integers, doubles, meaning decimal numbers, or characters, meaning strings. And lists, on the other hand, they are actually determined. Their essential feature is that they can contain elements of different types. Some of the central takeaways you should definitely keep in mind is that you can test for the types by using the function typeof or the is family of function. You can coerce an object from one type to another using the as functions. You should remember how to index them. In the case of atomic vectors, you use single square brackets. For lists, you need to use single square brackets if you want to have an element of a list as type list. But if you want to have the underlying data structure, you need to use the double square brackets, or you can use the abbreviation using the $sign. You should also remember actually some useful helper functions when creating vectors in the first place. So if you want to repeat certain elements, you can use rep. If you want to concatenate words, you can use paste. If you want to create sequences, you can use sec. And this is actually very useful in practice. You also should remember about the concept of vectorization, which is very useful to speed up computations in R. And you should also remember the strange data types like NA, null, or NaN that come up frequently. As I already indicated in the beginning, it is very important to learn about these different fundamental data types because functions work differently on different data types. And the other thing is that these fundamental data types we encountered today are the basic for more complex data structures such as vectors or data frames. But this is something we will deal in one of the future sessions. For right now, it is important probably to wrap up what we've learned here, to do the exercises and to make sure that you remember these foundational elements of R, which you will encounter all over the time, even if you're dealing with very advanced concepts. These fundamental data types you learned about here in this session, they remain important over the whole time you're using R.